Hello everyone, myself Dr. NCH Ramgopal, working as Associate Professor in Mathematics, Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all today's presentation on goodness of fit test. Let us recall the previous session. In the last session, we have discussed the test of hypothesis concerning several proportions. In test of hypothesis concerning several proportions, we test whether all the proportions are same or not. So, the null hypothesis, all the proportions are same, is tested against the alternative hypothesis, all are not the same. And in test of hypothesis concerning several proportions, we apply chi-square test. And also we solved some problems on several proportions. And coming to today's presentation, today we are going to discuss introduction to goodness of fit test, fitting a theoretical distribution for the given frequency distribution table, then goodness of fit test, and conditions for validity of chi-square test and problems on goodness of fit test. Now, chi-square test is used to determine if a population follows a specified known theoretical distribution such as binomial, Poisson and normal, etc. In goodness of fit test, we apply the chi-square test, and hence this chi-square test is useful to test whether the given data best fit a theoretical distribution or not. So, here to assert how closely the actual distribution approximates the assumed theoretical distribution, we apply chi-square test. And also the test is based on how a good fit is there between the observed frequencies, that means Y's given in the problem, and the expected frequencies that we are going to calculate denoted by EIs is known as goodness of fit test. So, the test based on how good a fit is there between observed frequencies and expected frequencies is known as goodness of fit test. This test judges whether the sample is drawn from a certain hypothetical distribution or not. That is, the same thing can be explained as whether the observed frequencies follow a postulated distribution or not. A frequency distribution table will be given. Now, we need to test whether a good fit exists between the given data and a theoretical distribution. And statistic chi-square is a measure of discrepancy existing between the observed and expected frequencies. First, we fit the theoretical distribution. So, first we fit the theoretical distribution in which the expected frequencies will be calculated. So, expected frequencies means EIs. EIs will be calculated to the given frequency distribution in which the observed frequencies will be given, OIs. So, these OIs will be given in the problem and we calculate EIs, and using these two values we test whether the given data, if there is a best fit exists between the given data and a theoretical distribution. So, this test is called goodness of fit test. Now, fitting a theoretical distribution. A frequency distribution table as shown in the given table will be given. Here Xi's and frequencies, given frequencies which are the observed frequencies. So, the values of X are X1, X2, X3 and so on Xk, and corresponding frequencies are F1, F2 and so on Fk. So, this frequency distribution table will be given. Now, we need to fit a theoretical distribution to the given distribution table. For example, fit a binomial distribution, fit a Poisson distribution or fit a normal distribution to the given data. To fit a theoretical distribution, first we find the total frequency which is denoted by capital N, and that is given by capital N is sigma f of xi. So, let us add all these values f1 plus f2 plus so on fk, that is the total frequency denoted by capital N. Now, for the above frequency distribution, first calculate the probabilities using a theoretical probability distribution. For example, if it is required to fit a binomial distribution, then let us use the formula P of x equal to x is NCX P power x Q power n minus x. Let us use this formula where x from 1, 2 and so on, since k values are given 1 to k. So, find all the corresponding probabilities, that is the second one. Next, find the expected frequencies by multiplying each probability with the total frequency. So, Here in step 2, we have obtained the probabilities using, for example, binomial distribution. Now multiply each probability with the total frequency capital N. Then we can obtain the expected frequencies EIs. So finally we construct this table, the given values of X, and these are given observed frequencies or given frequencies in the frequency distribution table. Then we find the probabilities corresponding to each X value, X1 for X1 P1, X2 P2 and so on Xk Pk. And then we find the expected frequencies by multiplying the probabilities with total frequency N. So denoted by O1, O2 and so on OK. So construction of this table from the given frequency distribution table is called fitting a theoretical distribution. For example, if it is required to fit a Poisson distribution, then we'll use the formula of Poisson distribution, probability of X equal to e power minus lambda, lambda power X by X factorial, and use this for different values of X, 1, 2 and so on K. Find all the probabilities, then multiply with total frequency N. That gives the expected frequencies. So for the given frequency distribution table, first we find the probabilities using the corresponding probability formula, then multiply each probability with total frequency so that we can obtain the expected cell frequencies. So these are expected cell frequencies E1, E2 and so on Ek. Now coming to the goodness of fit test. Here we test the null hypothesis H0. A good fit exists between theoretical distribution and given data. Between a theoretical distribution and a given data, there exists a good fit. That is our null hypothesis. We test this against the alternative hypothesis. There is no good fit between these two. And we test this at 5% level of significance or 1% level of significance. And the critical reason is given by chi-square calculated is greater than chi-square alpha, then reject H0. Simply reject the null hypothesis if the calculated value is more than the tabular value. Since there is one and only one alternative hypothesis, we have one and only one condition. If the calculated value is greater than the tabular value, simply reject the null hypothesis. That means we have to accept the alternative hypothesis that no good fit exists between the given data and theoretical distribution. And here the test statistic follows chi-square distribution with k-1 degrees of freedom, with new degrees of freedom, and the calculated value is given by, this formula is also similar to the testing of hypothesis concerning several proportions, but there we have two categories, successes and failures. So I, J, two values are there, whereas here we have only the observed cell frequencies OIs and expected cell frequencies EIs. So the formula is chi-square calculated is given by sigma I equal to 1 to k, since there are k values are given, OI minus EI whole square divided by EI. Simply the difference between the observed and expected frequencies, calculate that first and square the values, and sum of the squares of differences between observed cell frequencies and expected cell frequencies divided by expected cell frequencies. And here this chi-square follows new degrees of freedom, follows chi-square distribution with new degrees of freedom. And how to find this new? New is the degrees of freedom. There are two different things. The first one is new is k-1. K is the number of values given in the distribution table. If EIs are calculated without having to estimate population parameter. So if we are not estimating any single population parameter to find EIs, the expected frequencies, then nu will be k-1, the total number of values given minus 1. Second one, nu will be k-m-1 if we are calculating m population parameters to estimate EI. To find the expected frequencies, if we need to calculate m population parameters, then nu will be k-m-1. If we are not calculating any population parameters, simply we consider the degrees of freedom as nu equal to k-1. So these are the steps involved in goodness of fit test, and there are some conditions for validity of chi-square test. One of those points is sample size should be large, the number of classes k should be neither too small nor too large. So, k value should be between 4 and 16. It should not be a larger value or a smaller value. And OIs are, if OIs are small, if the given observed frequencies are small, that means less than 10, then combine neighboring frequencies to make it more than 10. For example, 5, 2, 1 like this, the observed frequencies are given, OIs. So, some values and last 3 values are 5, 2, 1. Then we combine these 3 because 5, 2, 1 these are less than 10 values. So, 5 plus 2 plus 1 which is 8. We can consider this 8 as a single observed cell frequency. So, combine neighboring frequencies to make it more than 10. Now, let us discuss one problem on goodness of fit test. Test for goodness of fit for a Poisson distribution at 5% level of significance to the following frequency distribution. So, a frequency distribution is given, x values are given from 0 to 8 and f of x, these are the given frequencies which can be denoted by OI also, Fi or OI, these are the observed frequencies. So, this is the experimental data given. Now, we need to test whether there exists a good fit between this data and Poisson distribution, that we need to test. So, that means we have to use Poisson distribution formula to find the corresponding probabilities. Now, coming to the solution, consider the given data, x values and corresponding frequencies, observed frequencies. First, calculate the total frequency. Total frequency n is given by sigma Fi, where I equal to 0 to 8, total 9 values are given. So, 52 plus 151 plus 130 plus so on 2, this is equal to 500 in this particular example. Now, here we have to test whether a good fit exists between the data and Poisson distribution. In Poisson distribution, what is the formula to find probability of x successes? E power minus lambda power x by x factorial. Here lambda is only the parameter in Poisson distribution. If we have this value of lambda, we can calculate any probability at any value of x. So, first we need to find this probability, first we need to find this value of lambda. To find this, since the frequency distribution table is given, we can find the mean or average of the given frequency distribution table using the formula mu equal to sigma xi oi by sigma oi. That means, let us multiply the corresponding values of x and frequencies and add all such values divided by total frequency. Sigma oi means the total frequency, which is 500. So, 0 into 52 plus 1 into 151 plus 2 into 130 and so on plus 8 into 2, that becomes 1010 divided by the total frequency 500. So, we got the mean of the given frequency distribution is 2.02. And also we know that the mean of Poisson distribution mu is lambda. So, here already we have calculated mu value as 2.02, hence the value of lambda is 2.02. So, we have obtained that parameter of Poisson distribution. If we have this value of lambda, we can calculate any probability. So, let us use the formula. Probability of x successes is e power minus x lambda power x by x factorial. So, we need to find these probabilities for different values of x from 0 to 8, total 9 probabilities we need to calculate. So, use the same formula to calculate all those probabilities. So, by using the Poisson distribution formula, we have obtained the probabilities, probability of 0 successes 0.1326, 1 success 0.26796, 2 successes 0.2706 and so on. we can calculate all the 9 probabilities. Now let us multiply these probabilities with the total frequency n equal to 500, which gives the expected frequency. So expected frequencies EIs are given by probability of x successes multiplied by n. So x values, observed frequencies, probabilities, and the expected frequencies which are calculated using this formula. So we have obtained the expected frequencies as 66, 134 and so on. Here the total will be 500 and here also the total will be 500. Now you can clearly observe in the expected frequencies the last 3 values are less than 10. According to the condition for the chi-square test, since these values are less than 10, we combine these 3 values and use it as a single value, 6 plus 2 plus 0, which is 8. And now the test is as follows: null hypothesis H naught. So a good fit exists between the given data and Poisson distribution, or Poisson distribution is the best fit for the given data. And we test this against the alternative hypothesis, no good fit exists. No good fit exists. So there is no good fit between the data and the Poisson distribution. And level of significance 5%, so I can use it as 0.05. Critical region, reject H naught if chi-square calculated is greater than chi-square alpha. Chi-square calculated value is more than the tabular value, we can reject the null hypothesis. And here total number of values k is 9 and lambda is the parameter that we use in Poisson distribution, and we have calculated that value lambda first to find the expected frequencies. So m equal to 1 and hence nu is or k minus m minus 1 degrees of freedom. So k is 9 minus 1, so 7 degrees of freedom. From chi-square table, chi-square 0.05 for 7 degrees of freedom. This value is given by 14.067. This can be obtained from the chi-square distribution table. Now coming to the calculation part, here the test statistic is given by chi-square calculated is sigma I equal to 1 to k OI minus EI whole square by EI. So we have observed cell frequencies, expected cell frequencies. So let us calculate this value, sum of squares of differences between observed and expected frequencies divided by EI. So this results as 9.2419. So you can substitute all the values here for each I equal to 1, 2, 3 and so on k. Here how many values are given? I equal to 0 to 8, total 9 values are given. So you can find this summation as sum of 9 values, and which results as 9.2419. And the final decision, here this is the tabular value and this is the calculated value. Let us compare these two. Since 9.2419 is less than 14.067, chi-square calculated is less than the tabular value. The calculated value is less than the tabular value. Hence, if the calculated value is greater than the tabular value, we reject the null hypothesis. But here we got less than. So we cannot reject the null hypothesis. Hence, we have to accept the null hypothesis H naught, that there exists a good fit between the given data and Poisson distribution. So this is the final conclusion, and the goodness of fit test is used to test whether a good fit exists between the given data and the theoretical distribution. In this particular example, between given data and the theoretical distribution, Poisson distribution, a good fit exists. That is the final conclusion. Similarly, let us consider another example. Test for goodness of fit of a binomial distribution to the following data. So again the values are given, x values and corresponding frequencies are given. This is F, corresponding frequencies are given. So, these are OIs, and let us calculate total frequency first, and N, here 6, we can consider this table as 6 coins are tossed, that is the experiment. If 6 coins are tossed and X denotes the number of heads, maximum 6 heads are possible, or 5 heads and 1 tail, 4 heads and 2 tails, and so on. 0 heads, that means complete failure case, all 6 tails. So, the experiment is tossing 6 coins. That is why I have taken n equal to 6. And what about these frequencies denote? Out of 80 times, 4 times we got 6 heads, 6 times we got 5 heads and 1 tail, 7 times we got 4 heads and 2 tails, and so on. So, here small n is 6, capital N, the total frequency is 80. By adding all these observed frequencies, we can get this value. And here we need to fit a binomial distribution first. So, by binomial distribution, the formula is NCX p power x q power n minus x, q power n minus x. So, p of x equal to x is NCX p power x q power n minus x for different values of x 0, 1, 2 and so on 6. Total we need to find 7 probabilities, and to apply this binomial probability, first we need to know what is n and what is p. These two values are the parameters of binomial distribution. N and p are the parameters of binomial distribution. Similar to the previous Poisson distribution, lambda is the parameter of Poisson distribution. Here n and p are the parameters of binomial distribution. This n is given in the problem, but we do not know what is this probability of success. So, first we need to calculate the probability of success p. To find that, let us calculate the mean of the given frequency distribution table using sigma xi into oi divided by total frequency, and this results as 2.4. So, here the calculation is 0 into 5 plus 1 into 18 plus 2 into 28 and so on plus 6 into 4 divided by total frequency is 80. That results as 2.4. And we know that the mean of binomial distribution, is mu equal to NP. The mean of binomial distribution is mu equal to NP. So, let us equate mu equal to NP equal to 2.4. But what is the value of N? 6. 6P is 2.4. So, P results as 0.4. If we have P, you can find Q also 1 minus P 0.6, and the test is as follows. The null hypothesis H naught, a good fit exists between the given data and binomial distribution. No good fit exists, and the level of significance 5%, so 0.05. Critical region, reject H naught if chi-square calculated is greater than chi-square alpha. Here, how many values are given? K equal to 0 to 6. So, 7 values are given, and M, the number of population parameters that we have obtained to estimate EIs are 2, N comma P are the parameters. So, nu equal to K minus M 1 minus M. So, which is 7 minus 3 for 4 degrees of freedom. So, for 4 degrees of freedom, chi-square 0.05 from chi-square distribution table, this value is 9.488. This is the tabular value. And here, using this binomial distribution formula, we can first calculate the corresponding probabilities P1, P2, P3 P4 and so on, and then we multiply each probability with total frequency, and we have obtained the expected frequencies EIs or PIs into total frequency, and we got 4, 15, 25, 22, 11, 3, 0. So these are the values that we got after multiplying each probability with total frequency, and already observed frequencies are given in the problem. So let us substitute all here, and after simplifying, this chi-square calculated value results as 6.39. So this is the calculated value, and 9.488 is the tabular value. And once again, since 6.39 is less than 9.4888, chi-square calculated is less than chi-square alpha. If calculated value is more than tabular value, we reject null hypothesis. But here calculated value is less than the tabular value. Hence, we have to accept the null hypothesis H0, that a good fit exists between the given data and theoretical distribution, binomial distribution. So like this, we test the goodness of fit test for the given frequency distribution table. And summary of today's session. In today's presentation, we discussed the goodness of fit test and how to fit a theoretical probability distribution for the given frequency distribution, and also conditions for the validity of chi-square test and the exact test for goodness of fit. And in the next session, we will discuss ANOVA, the analysis of variance. Thank you.